Now there is one result that we quite often use in complex numbers. Now let's say we have two complex numbers. Z1 is x1 plus iy1, then Z2 is x2 plus iy2. Then if I tell you that Z1 is exactly the same as Z2, that means the two complex numbers are the same, then what it means is the real part of Z1 must be the same as the real part of Z2, and the imaginary part of Z1 must be the same as the imaginary part of Z2. Okay, so that means two complex numbers are equal if and only if both their real and imaginary parts are the same, are equal. Now let's take a look at how we use this result in example 6. Now in example 6, I want to find the real numbers a and b such that a over 2 plus I plus b over 2 plus 3i is equal to 4 plus I. So what I'll do first is I'll tell myself, let's combine everything on the left hand side to make it a single fraction. So I'll get 2a plus 3ai plus 2b plus bi divided by 2 plus I 2 plus 3i equals to 4 plus I. And if I multiply the denominator on both sides, I will get 2a plus 2b. Okay, I'm grouping the real parts together, and I'm grouping the imaginary parts together now. 3a plus b equals to 4 plus I times 2 plus I times 2 plus 3i. Now I can use the GC to help me to compute the right hand side. Okay, if you use the GC to compute the right hand side, you will have minus 4 plus 33i. Then the result above says this: if these two complex numbers are the same, then their real parts must be the same, and their imaginary part must also be the same. So we say, we compare real parts. 2a plus 2b is the same as minus 4, so I have the first equation. Then I compare the imaginary part. 3a plus b, okay, is the same as 33. So I'll leave the solving of this pair of simultaneous equation for you to try. In the end, you ought to get a is 35 over 2 and b is minus 39 over 2. Done. Now let us take a look at another example that utilizes this same result. Now example 7 says that z plus I is a root of this equation here. Now they want you to find the a and the b in this equation, where a and b are real numbers. So what I'll do is this: I will first give a name to this equation. Let pz equals to this. Then I'll say, since z equals to I is a root, by factor theorem, what do I have? I have pi is equals to 0. Now what this means is your I to the 4 minus ai cubed plus bi square minus 2i plus 5 must be 0. And I to the 4 is 1. I cubed is minus I, and I square is minus 1, and I have this equation, and I can simplify this to get 6. Okay, let's group all the real numbers together. 6 minus b. Alright, then let's group the imaginary parts together. I have a minus 2 equals to 0. Now 0 is the same as 0 plus 0i. So if this pair of numbers are the same, then what I must have is the real part must be 0, and the imaginary part must be 0 as well. So quite simply, just rearrange both sides. You get a equals to 2 and b equals to 6. Done. Now in example 8, we see the same result being used in a different context. Now the question wants you to find two square roots of the number 5 plus 12i. So what I'll do first is I'll give the square root a name, or rather I will define the square root. I'll say let a plus bi, okay, be the square roots, or the square root of the number 5 plus 12i. Then what it means is a plus bi is just this square root 5 plus 12i. Now I'll take square root on on both sides, and I'll get a square plus 2ab I plus b square I square equals to 5 plus 12i. Now if you look at the left hand side, what do you see? You see a I square. Now I square is the same as minus 1. This number is the same as minus 1. So if I group the real numbers together, what I'll have is a square minus b square. Now this is the real part, okay, plus the imaginary part 2abi is equals to 5 plus 12i, and the real part is 5. The imaginary part is 12. So all I need to do is to compare. So I'll get one equation here and another equation here, and the remaining part is just to substitute and get your values for a and b. So let's run this through. I have 12 equals to 2ab, so I can rewrite the whole thing by saying that b is the same as 6 over a. So I'll sub the 6 over a back into the first equation. So I'll end up getting this line. Simplifying by multiplying by a squared throughout, I will get this equation, which I can factorize. Now because a is real, your a squared plus 4 is always positive. So that means I can divide by this number on both sides, leaving us with just a squared minus 9 equals to 0. And once I have this, I will just take square root on both sides to get a is 3 or minus 3. If a is 3 or minus 3, that gives us b to be 2 or minus 2 based on this result. So the square root of 5 plus 12i is plus minus 3 plus 2i. Now, one thing I want to stress here is this. Now your a is plus minus 3 and your b is plus minus 2. Now you cannot write your answer like this, plus minus 3 plus minus 2i. This is wrong, because this gives you actually 4 different answers. 3 plus 2i, 3 minus 2i, minus 3 plus 2i, minus 3 minus 2i, which is wrong. There are only 2 answers. So do not write your answer like this. Now, if you use the GC, now your GC will give you the answer 3 plus 2i. It will only give you one solution. But if you recall, whenever I have a number z equals to 4, for example, z squared equals to 4, for example, your z is always plus minus 2. Okay, we always add a plus minus in front. So your GC giving you one answer also tells you the other answer. So what you need to do is to remember to add a plus minus in front of your 3 plus 2i.